In the previous video, we talked about the problem that we faced based on the fact that we've got this mass univariate statistical approach going on. We are doing a very, very large number of multiple comparisons in order to draw statistical inferences. In this video, I want to talk to you about Gaussian random field theory and how that enables us to address this in a systematic and realistic way that's similar, at least conceptually, to what Bonferroni is doing, but provides a way of being a little bit less conservative based on the realities of the data that we're looking at. Okay, so the way to start this is to start by beginning and talking about resolution elements, or resels. I'm probably just going to refer to them as resels rather than resolution elements here out. And the point is that if we're just doing things on a voxel-wise level, the individual voxels aren't independent from one another. So if you have two voxels that are next to each other, they're probably both being fed by the majority of the same blood supply. They're probably both involved in some of the computations at the same time. I mean, the tissue that's adjacent to one another tends to be related to one another. So there are various reasons why the voxels aren't all independent. There's a relationship between nearby voxels. Some of that's the physiology that I've just mentioned, the blood flow, and in fact the neural computation. And some of it's due to like physics properties and image processing things that we've done. So there's something known as a point spread function in the way we actually collect the data with fMRI, which means that we can't be specific to this little 3x3x3 cube. There's a little bit of a spread there. And then in addition, there's all sorts of external smoothing that we've applied during image preprocessing. So in addition to the actual smoothing position where we smooth voxels into each other, we've also done a number of interpolation steps when we did realignment and when we did normalization. And both of those add smoothness to the data as well. So for all of these reasons, voxels aren't independent of each other. So if you were to have 250,000 voxels and do 250,000 correction using 250,000 in your Bonferroni, you're being too conservative because the data themselves aren't independent. If they were completely separate from one another, then sure, that would be the right thing to do. But that's not. So instead what we're going to do is we're going to try to measure how independent a set of voxels is. And the way we're going to do that is using resels. So it's a measure of how far away you need to move in 3 dimensions until the data that you're looking at are effectively independent of one another. Okay. And that means that the size of a resolution element will by definition always be larger than a single voxel. And it's going to depend on the smoothness of the data. It's going to depend on the volume of the data. And it's going to depend on the surface area of the data, the number of resels that we have. Obviously, the smoothness is going to make a difference. If you've smoothed it more, then you're going to have to move further away to get to independent data elements. If that happens, that means there are going to be fewer resels in your image than there would be if you had smoothed it less. Hopefully that makes a lot of intuitive sense. Similarly, volume is obvious, right? If you have a larger volume, then by definition you have more resels than if you have a smaller volume. Pretty simple. Surface area is the one that's actually a little bit counterintuitive, I think, for people. Because if you just had a sphere, that's the most compact way to have any given volume. But if you have something more complicated than that, then your resolution elements, which are effectively little spheroids, won't fit it very well, particularly at the edges. You'll get parts of resolution elements. But if you have a part, then you still have to count that resel, which means that if you have a more complicated surface, then of course you have more resolution elements. What that means for us in practice is that one of the things that people thought initially was, look, bold signal comes out of gray matter. It's not in white matter. It's not in cerebral spinal fluid. So anything that we find there is a false positive, kind of by definition. So maybe what we should do is not correct for the whole brain volume, but we should just correct for the gray matter volume, because that would reduce the number of comparisons that we were doing rather dramatically. The problem with that is that the gray matter is folded like a wrinkled cloth, and it has a very, very complex surface area, which means that the number of resels that fit in the gray matter is not significantly less than the number of resels that fit in the volume that the whole brain takes up. So it really doesn't help you much when it comes to doing statistical inference testing, correcting for the multiple comparisons problem. The key thing to remember here is that the number of resels in your sample, in your brain, depends on the smoothness of the data, the volume of the data, and the surface area of the data. And I want to try to illustrate this graphically rather than go into the math of all of this. And I'm going to do that using a series of 2D images because that's obviously all I can show. This is a little square with 128 values on the x-axis and 128 values on the y-axis, all of which have been chosen by random. So this is by definition noise, right? Again, this is just basic MATLAB code. Assuming I can find the MATLAB code that I use for this in my files, what I'll do is I'll put it up on Moodle for you if you care to play with it yourself and generate these images and play with the parameters and see how it affects them. Something I would definitely encourage you to do. But this is noise. In addition, it's spatially relevant, the fact that I've put it in an XY plane. You can now talk about individual voxels here having neighbors. They have a neighbor to their left, to their right, above and below them, right? As a result, there's a spatial configuration here. These aren't like reaction times in an experiment where I just have, I don't know, 20,000 reaction times for people over a group, where there's no relationship between any one reaction time and any other reaction time. They're independent of one another. That's not true here. Here there is a relationship, and it's because they're laid out in space. They have a spatial configuration. In this case 2D, but for fMRI it would be 3D. And now what I want to say is, look, how do I do statistical significance testing to see whether there's anything significant in here? And I can tell you in advance, there shouldn't be, because I know how this field was generated. It was generated by me creating these as independent random numbers, despite the fact they have this spatial configuration. Well, the most obvious thing is to say, well, there's like 16,000 numbers here. So if I want a 0.05 family-wise error, that is to say a 1 in 20 chance of saying there's something here that really isn't, then what I need to do is threshold this at a z is greater than 4.5. So I figured out what the corresponding p-value was and then converted it to a z-score so that it's a number that's much easier to talk about rather than x number of zeros and then something small. And that's characteristically what I'm going to do. I'm going to talk about these in terms of z-scores. And that would be the height threshold using a solely Bonferroni approach. I could make things easier on myself by taking that data set and smoothing it a bit, right? So I could, for instance, take 8 voxels along the x-axis, 8 voxels along the y-axis, giving me a little square of 64 voxels, compute their mean, and replace all 64 of those with their means. So that's what I've done here. I've reduced the data volume by just doing a very sort of square little smoothing algorithm. And what happens is I still have 16,000 points on my plot, but I've really reduced the number of independent measures from 16,000 down to about 256. So this is what I mean by there's a resolution element. Each of those squares is now a resolution element because those squares are the borders between independent measurements. And if I do that and then correct for the fact that I only have 256 independent measures instead of 16,000, that means that my Z height threshold for what counts as significant is going to be 3.5. So I've reduced it from what it was before, in this case by a lot. Z-scores are highly nonlinear. So a difference between 4.5 and 3.5 is a big difference, for instance. And this is an example of how smoothing changes it from these independent measurements to of voxels to resolution elements, which are not independent, and takes into account some of that spatial information in terms of the non-independence in XY. And of course, in fMRI, it would be in X, Y, and Z. I can do a fancier smoothing, though. So the thing about the smoothing that I did is it's kind of stupid. It leaves these sharp edges, and sharp edges make these transition points that are very arbitrary. Why did I do it at those 8 voxels and not like 2 voxels over? Wouldn't that change things rather dramatically? Yes. So therefore, it's not a great smoothing algorithm. A better way of doing it would be to, for instance, add a Gaussian blur. So if I took a normal distribution, which is going to give you a little kind of normal, and then sort of rotated it around in space to give me like a 2-dimensional version of that, so it's sort of almost a Mexican hat shaped sombrero kind of thing, I could then apply that smoothing kernel to each of the voxels or pixels in this data set and say, okay, well, I'm going to smooth it most by the ones that are right next to it and then less by the ones a little bit further away. And I could do this in X and Y. And the advantage to doing this is that I end up with this much smoother data set where it's less dependent on some of the assumptions about which exact chunks I've actually used. And this is what it would look like. And you can see, by chance, there are some darker areas and there are some lighter areas, and then there's some areas in between. And that's just the noise. But this now becomes what's called a Gaussian random field. That is to say, it's a field because it's got spatial characteristics. It matters who your neighbors are. And it's a Gaussian random field because they're random numbers that are smooth, and that smoothness is represented well by Gaussian smoothness. It doesn't have these abrupt changes from one to another that you wouldn't really expect. Turns out that there's actually a fair amount known about Gaussian random fields. So when imaging got to this point, they realized that there was already an existing literature about Gaussian random fields and how to characterize them and the things that we know about them. To some extent, this again comes from physics, but not really from the particle physics people so much as the cosmology people, right? The people who are interested in the structure of space. Space is well approximated by Gaussian random fields, where the measure is sort of the density of energy or the density of matter. According to physicists, they're the same thing, but for the rest of us, you might consider them as an or rather than the same. But for instance, there are these hot spots of massive density, like a star, or even more so like a black hole. And then there are lower areas of density, like planets, or even lower, like an asteroid field. And then the vast majority of things is basically empty. There's virtually nothing there. There's, of course, something. It's never completely empty. But the way that matter and energy are distributed can be fairly well described by Gaussian random fields. So this is something that mathematicians and certain areas of physics have looked at for a long time. And that's very, very handy for us because we can take advantage of some of the things that they already know about it. So for instance, the fact that we have these Gaussian random fields, because we've collected multiple data, the data has a spatial configuration, and the data are smooth. The data are smooth because intrinsically there's some smoothness to it, and then extrinsically we've added some smoothness by doing our pre-processing, both in terms of the interpolation that we've done, because anytime you interpolate the data set, you make it smoother, but also because of the external smoothness that we've applied. It's worth pointing out that sometimes people think the reason that we smooth fMRI data is to make it conform to a Gaussian random field so that we can do our inference. That's not correct. The reason that we smooth our data is to increase the signal to noise characteristics of our data. We do it in order to make the data more meaningful. As a result of that, Gaussian random field theory is something that we can do our inference based on, but we don't change the data to make it clever use of inference. That's not correct. It's just sort of inverting the causality there, and it's just worth being clear in your head. We smooth the data to increase the signal to noise in the data. As a result of that, and it's not the only smoothing that we've done, we end up with this Gaussian random field, and therefore we can use Gaussian random field theory to do our statistical inference. And as we've talked about, a heuristic is that we smooth the data at about twice the smallest voxel dimension. So typically, if you have a 3 by 3 by 3 voxel, you use something on the order of 5 or 6 millimeters of smoothing. Typically, it's about 5 to 8 millimeters of smoothing across most studies. It's not the only smoothing step. There's both intrinsic and extrinsic aspects of this smoothing that means that we have data that approximate a Gaussian random field. So in terms of visualizing this, obviously I've shown you this Gaussian random field here on the left. It's random noise that I've smoothed using a Gaussian filter. But another way to visualize this is shown on the right as more of a 3D plot. So what I've done in this case is I've colorized the heights. So things that are sort of bright on the left show up as peaks on the right. And you can possibly see there's a peak, which I'll illustrate here in the video, that you can see as these bright red. Whereas the dark areas are troughs that end up being blue, and things in the middle are sort of this light blue-green. And it's useful to be able to visualize the data in different ways, which is why I'm doing this. Because now that we have this kind of mountainous visualization, we can look at how we would threshold this. If we were to just, for instance, put a plane across it, we can see which peaks exceed that by chance. And that's exactly what I want to do. So for instance, if I wanted to choose an arbitrary threshold, just say, look, the values on the z-axis here up are z-scores, just to make life simple, right? Then what if I put a threshold on this and said, well, what if I thresholded this at a z of 2.75? What you can see right away is I put a plane at that level, and that plane is just bright red. And anything that exceeds that plane comes through that threshold. You can see that in this case, there are two peaks that do it. In other words, there are two things that are occurring by chance if my height threshold is z of 2.5 or 2.75, excuse me. Which means that wasn't a great way to pick my threshold, because clearly I have at least two false positives in this case. And the question that we ask here is, how do we choose that height threshold so that we only get 0.05 peaks exceeding it by chance? That is to say, there's a 1 in 20 chance that any given peak will be present after we do the thresholding. And that's the problem that we're trying to solve using Gaussian random field theory. These are the two peaks that exceed it by chance. I'm sure it's obvious to see them. Another visualization that's going to be useful is imagine looking down at that plane. And now what I've done is I've replaced anything that exceeded the threshold by chance with white and everything else with black. And I'm going to call that the excursion set. So that's what's shown on the right. You can see those two peaks over there, and they are what's past my height threshold. Recall that I picked this height threshold arbitrarily. I just said, what would it be if I went with 2.75? Let's do some better than that. So clearly 275 wasn't a good option. It was too lenient because I got two big false positives. What if I just bumped it up? What if I said, well, what if I use a height threshold of 3.5? That would be, bearing in mind that it's very nonlinear, that's a big increase in my height threshold. Is it better? Yes. Now there's only one thing that's exceeding it by chance. But the fact that there's still one indicates that it's not awesome because it's still a false positive, right? So what is the right way to do this? In this case, what we can turn to is something known as the Euler characteristic. So Leonhard Euler, I have no idea why he developed this math, but he developed it in the early 18th century. And it was the probability that if you threshold a Gaussian random field at a given height, the number of sort of independent clusters that will exceed that threshold. I'm sure this was theoretically an interesting question. I can't imagine what practical application he had at the time. But what you see is you get this kind of a curve that's shown here. So that is to say, at a low threshold, everything exceeds it. So you get sort of about one big cluster. But as you raise that threshold, that cluster starts breaking up and you get lots of thresholds, up to the point where now you're getting to the point where it's even getting higher, and some of those thresholds, some of those peaks are below the threshold, and you start to have this reduction in the number of peaks. Well, if you just sort of focus on the right-hand part of that curve, the part here I've shown in red, then what you could do is say, well, when it reaches 1 again on the right-hand side, from 1 to 0 is actually going to approximate probabilities. So what I could do is say, well, what is the height threshold that I need to have 0.05 thresholds occur by chance? That is exactly what we want, right? We want to be able to say, I want a 1 in 20 chance that if I threshold this Gaussian random field, I will get something that's active but is only there because of chance. That's my false positive rate. But given that Euler created this characteristic, this equation, we can actually solve it. We can say, well, what if the expected height threshold is 0.05? What is the height threshold that corresponds to that? And for this particular Gaussian random field, it is a z of 3.9. So my 2.75 and my 3.5 that I just picked randomly weren't great picks because I did it just ad hoc. But I can solve this problem numerically and find out what the correct height threshold is for this Gaussian random field. And I'm sorry, I'm being specific in saying for this random field because, as we said before, the random field characteristics depend on the smoothness of the field, the volume of the field, and the surface area of the field, right? Those are the things that are going to affect the number of resolution elements in there. So it's not that a 3.9 always corresponds to a correct height of 0.05. Not at all. It depends on the specific data set that you're looking at. But given that Euler has created this equation, we can solve this, and we can solve it for any particular data set once we know the number of resolution elements in that data set. The reality is you are not going to be expected to solve this. The software is going to do this for you when you decide that you're going to take a height threshold based on a particular family-wise error that you want in your analysis, typically 0.05. And as I said, what this means is that for this particular data set, there's a 5% chance or 1 in 20 chance that anything that's greater than 3.9 is just a false positive. That means that anything greater than 3.9 we would probably accept as a legitimate effect because we accept that 5% risk. So to just reiterate this, I mean, one of the things that's important to bear in mind here is that the volume very much affects the threshold. So this is a much smaller random field. So previously I had 128 by 128. This is only 64 by 64, which means that it's a quarter as large. That is to say there's a quarter as much volume. If we then draw the Euler characteristic for this curve and then focus in on that tail bit as it goes from 1 down towards 0, then the height threshold that corresponds to a 0.05 p-value is actually 3.6. And again, this sort of illustrates some of the nonlinearity of this. So despite the fact that this volume is only a quarter as large as the one before it, there's a very small reduction from 3.9 to 3.6 in terms of what would constitute the correct height value to correct for the multiple comparisons and the number of resolution elements here so that you still maintained a false positive rate of 1 in 20. This is important, particularly important for fMRI, because you might think, well, look, if I have to get a Z-score of like 5 or something with a whole brain comparison, then anything I can do to reduce that volume is going to make a big difference. And that's roughly true conceptually, but it's not going to make a big difference. So for instance, if you said, look, actually, this is a language task. I really only care what's happening in the left hemisphere. I'm going to ignore the right hemisphere and reduce my volume by half. You might think that'll really reduce the statistical threshold you need, but in fact it won't. Because it's such a nonlinear drop-off, reducing the volume by half is going to reduce it a little bit. You maybe go from 5 down to 4.8, 4.7, something like that. But it's not going to give you the massive increase in sensitivity that you would hope for. So you just need to be aware that when you're going to use volume as a characteristic that's important in reducing the number of statistical comparisons, we're going to start talking about small volumes, typically on the order of a couple to a few cubic centimeters, not half a hemisphere or like a frontal lobe or something like that, because the savings that you get by reducing the volume won't really translate very well into height threshold savings. Smoothing is also important because the more you smooth the data, the lower the statistical threshold you need. And this again should be fairly obvious from what we've talked about. This is that same 64 by 64. And you can see in the slide before, it's a little bit spiky. Here I've simply smoothed it more. And when you smooth it more and calculate the Euler characteristic, then you find that this makes a big difference to decreasing the statistical threshold. Why? Because increasing the smoothing decreases the number of resolution elements. That is to say, each of the resolution elements, the resels, is larger because there's more smoothing, which means there are fewer of them in the whole volume. So one of the ways to decrease the statistical threshold you need is to increase the smoothing that you apply to your data. One note of caution here. This is very much true in general, but it can be misused by sort of searching through your data space. So that is to say, imagine that you've run your experiment, you see some things that look really interesting, but in fact they're just below the statistical threshold that you need for whole brain corrections. and you think, okay, well, look, I followed Joe's advice. I smoothed the data at 5 millimeters during my pre-processing phase. All I need to do is smooth it at 8 millimeters now, and that activation is likely to reach significance because my statistical threshold will decrease. Two problems with this. One is this is essentially fishing in your data. You've already looked to see what your data look like, and then you're changing your data to try to make it significant. And that is not considered best practice by any stretch of the imagination. But the other thing is, it depends on the size of the activation. If it was a fairly small activation, like it was in a more focal area, like for instance, you were looking at a thalamic nucleus that you thought was really interested in this particular task. Well, those activations aren't large to begin with. If you smooth it further, you may very well smooth away the activation because there isn't a large area to increase the height of the activation. It would be very different if it was some sort of large dorsolateral prefrontal activation where the 3 millimeter difference in smoothing is going to increase the strength of the activity. If you have something that's focal and you increase the smoothing, then you make it less likely to reach the statistical threshold as a result of that. So just beware of this. It's important to understand it, and I would absolutely recommend that you play with it ad nauseum to try to understand what's in your data. Change the smoothing, look at how it affects the height threshold, look at what's significant and what isn't as a result of these things. But when you're reporting data for a talk or a conference or a paper, beware. There's a right way and a wrong way to do this. And the right way is to use the heuristic at the beginning before you look at your data and choose your smoothing kernel. Not to then look at the results and then tweak your smoothing kernel to make your data significant. That is essentially a dishonest way of getting significant results. Okay, so I've talked at some length about Gaussian random field theory. The version that we've talked about here allows you to create what are called voxel thresholds. That is to say, it gives you, based on this Euler characteristic and the Gaussian random field theory that you're applying it to, Gaussian random field, that you're applying it to, you get a height threshold that can be applied at each voxel in order to control the family-wise error. So that is, any voxel that exceeds that height threshold is by definition significant. It may be that you end up with a single voxel above that threshold, in which case you've got a significant result by definition, but it may be very difficult to interpret because a single voxel that's a level of specificity that would be hard to sort of make much out of. You would normally expect that there should be some cluster of voxels that exceed this area by chance in order for it to be treated as meaningful. But that's not what voxel-wise threshold says. All it says is any voxel, any single voxel that exceeds the threshold is significant. That makes it very anatomically precise. You can say with confidence that each and every voxel at whatever their coordinates is that exceeds it is a reliable effect. So you can be very detailed in terms of the anatomy that you're presenting. And conceptually, this corresponds very closely to that sort of Bonferroni correction. We're not correcting by the number of voxels in this case, but really by the number of resolution elements. And when we do that, it's essentially a Bonferroni correction. A little bit complicated the way we calculated the resolution elements, but nonetheless, it gives you conceptually the same thing. The other thing that's really strong about this is that it's a completely automatic method. You calculate the Gaussian random field from the data that you have after pre-processing. We can measure the volume, we can measure the smoothness, we can measure the surface area. So we're not making any arbitrary decisions here. All of this key values are calculated directly from your data. And that's very, very powerful because you haven't introduced any realm for sort of fiddling your data. Everything is automated. You don't have any choices. The disadvantages to a voxel threshold are sometimes it can hide sort of large, maybe anatomically meaningful areas of activation that don't quite reach the statistical threshold. So that is to say, if you were maybe expecting something in dorsolateral prefrontal cortex, and in fact there's a really large blob there at like a Z of 4.5, but your statistical threshold for this data set is 4.7, that's a frustrating state to be in because you think, 4.5 is a pretty whopping signal. It's just not quite reaching threshold. maybe the fact that it's not just random voxels, but the fact that it's anatomically meaningful and in an area that I anticipated from the beginning suggests that I should use some sort of more lenient statistical threshold. So that can be a frustration. And some people have argued that as a result of that, because there's extra information there in the spatial configuration, the fact that there are anatomical areas that are relevant, sometimes voxel-wise thresholding is seen as not as sensitive to true activations as it could be. So in other words, it's yes, you're protecting your false positive rate, but you're doing it at the cost of your false negative rate. There may be real things going on that you're not accepting as real because you're being too stringent in your statistical thresholding. And this is always an issue. Anytime you do statistical thresholding, you need to trade off false positives against false negatives. However, the accepted criteria in the field is that we're really only going to worry about false positives, and we're going to do it with a family-wise statistical error of 0.05. As a result, the normal response from the field is if your data don't reach that threshold, your data aren't reportable as is because there's nothing of interest, and you either need to collect more data or you need to design an experiment that will be more sensitive to the true effects that are there. So at some level, the community response is, it's on you, buddy. Get it right, do the science better, but don't try to fiddle with your statistical thresholds in order to make things more lenient just to show us something that you didn't get right to begin with. That may or may not be the right way to approach this, and there's a whole interesting area about inference and what's right and what's wrong, what approaches could be done. But for our purposes, it's important to know that that is the default characteristic of the community, and that's probably the situation that we find ourselves in. There are other solutions. I'm not really going to get into them this term other than to talk about cluster thresholding, which will come up in the next video.